This is KBYP bringing you the Midas Touch, like the bumper music lead-in. I'm going to show you how to use these Eimac plate curves and the Eimac tube data and the Eimac tube calculator correctly. I have spent hours and days screwing with this, and the unbelievably horrible job that Eimac has done in presenting this information, especially in the care and feeding document, and finding a horrific mistake. They've done something in here that just destroys all this, and I'm going to show you what it is. It's very simple. It's a matter of editing. They've reproduced the care and feeding and reproduced this tube computer and made a horrible mistake that makes the results absolutely useless. These are called plate curves. In testing, they vary grid voltage, filament to grid on the left, against plate voltage, and they generate different curves which represent current. This is a complicated curve tracing job. And this is for the 8163 3-400Z specifically. I happen to have that exact tube, and I'm designing an amplifier to use it. Under no circumstance use a graph for a different tube. It won't work. This will be a Class B grounded grid. It must be constant current characteristics for the grounded grid for that tube. Never, ever try to substitute a non-power grid tube in an application like this, because if you do, I promise when you give it 100 watts from a 50 ohm transmitter, which corresponds to a 100 volt grid swing at tens of watts, the grid in that tube will turn into ashes in the bottom of the tube envelope. This is a power grid tube. It's rated at something like some fraction of 45 watts maximum signal driving power. And the actual into the tube is something like a bit less than half of that. I'll explain later why that is. But no, the tube isn't taking 45 watts. The transmitter has to be transmitting about that into 50 ohms to swing the tube, so to speak. If you try to follow Eimac's process for laying out a load line on this set of plate curves, you'll get hopelessly lost. I understand tube theory, and I got completely lost until I threw my hands up and said, I'm going to start over and I'm going to figure it out on my own, and I did, and it works much better. It's not enough just to draw a load line on a set of plate curves like that, because what I'm doing in particular is I've chosen one of these operating cases, typical operation minimum distortion products, for a plate voltage of 2 kV, because I have a 3 kV power supply at an amp and a half. So that will have plenty of overhead to drive a 2 kV amplifier. And at first glance, it looks like we can take these numbers and go put an amplifier together. Not going to happen. Basically, the only two things on here we can hang our hats on are 2 kV plate voltage max and the load impedance of 2750 ohms. The rest of it is obfuscated. The goal of what I'm doing in completely redesigning an amplifier, and I mean calculations all, is to find a way to transfer this information over to here, and that's not in the books. Somehow the load line that appears on this graph must agree with that information in that case, and it has to, because these are the tube characteristics that become these measured performance characteristics when that tube is put in a test fixture. So it's guaranteed that there's a link between the two. They don't tell us how to get there, and it's complicated. What's meant by a load line is, for example, the solid dark line starting at the 2 kV plate intercept and going up to the left. This straight line is the so-called load line. That represents a particular set of operating conditions. 2 kV maximum plate, some minimum plate voltage, which is 500 volts, and that represents, in different parts of the operating cycle, different currents. Different plate currents over here, and different grid currents there, and there's no screen, so no screen current. There can be a very large number of lines that can be drawn. There are three of them there in my process of trying to figure out the correct one. From geometry, a line requires 2 points to be defined, but they must be the correct ones to satisfy that on here. You'll have an awful hard time getting there with the horrifyingly screwed up way that Eimac presented this in Care and Feeding. They just took an elegant topic and butchered it. But I'm going to show you the correct way to do it. The first step is we have to understand the basic operation of the tube amplifier. This will be a class B, which means the conduction cycle, or the number of electrical degrees through which a tube conducts electricity, is 180 degrees, half cycle. Here's the critical concept. Over half the cycle, the tube plate is dissipating power. Over half, it's off, and it's cooling, or not dissipating. How do we know these numbers? We know 2 kV, not as a maximum, but as a case figure for this typical operation with 2000 volts DC plate supply. And we know 400 watts from the tube number, 400. 3-400 means a plate can dissipate 400 watts steady state. That's the maximum average plate dissipation. That's how hot the tube can get before it's damaged, in theory. Over an individual operating cycle, which you can find by taking the frequency, inverting it to get time, and take the frequency and invert it, and that gives time per cycle. If it's a million cycles per second, then each cycle is the inverse of that, and 1 times 10 to the minus 6 seconds. At the 80 meters, it's down in nanosecond range, but this cycle time is very short. So the exact dissipation over that cycle is extremely small, but all those million cycles per megahertz add up over a second to be a max of 400 watts. So that's represented as peak going up plus a peak going down all the way across. In the class B, this half cycle is doing nothing. Or it could be drawn upside down with this half doing something and the other doing nothing. But that means that 400 watts can be dissipated during the on, or the amplifying half cycle, times 2. Because the energy is not being input to the plate over this half cycle. So the working half cycle, if you will, can now be 800. Like that. 800 watts over a half cycle. From Ohm's law, ignore my chicken scratches, but power equals volts times amps. So amp equals power, 800 watts, over 2 kV, 400 milliamp. So that maximum dissipation at that maximum voltage is 400 milliamp. That means that over the operating half cycle, the plate voltage with a tube drawing no current is 2 kV, and at maximum current, just assume the plate voltage goes to 0 for a 2000 volt swing. It is not and cannot be that way in operation, else it will be horribly distorted. But this is an initial assumption to help us get a line on a piece of paper. The Care and Feeding document and my experiments with the Drakes shows that the efficiency of a Class B amplifier is about 66% according to Eimac. In the Drake TR3 and TR4, it's about that. It's 3 tubes at a total of 52.5 watts dissipation. The wattmeter reading is 150. The accurately measured PEP and CW is 298. So you can calculate that out as to the percent efficiency. That means the tube dissipates 33%. That's a third. So invert that third times 3. And in the Care and Feeding, they use a Class C example of 75% efficiency, so they multiply the maximum current by 4 in their example. In this example, with a 33% consumption by the tube, we multiply the input current by 3, which is 400 milliamps times 3, which is 1.2 amp. That gives a target, a reasonable calculated approximation of maximum plate current, which will appear on this graph, right in between these lines, between 1.0 and 1.4 amp, and between 1.2. So over here, someplace, somewhere over here, we're going to have to mark a dot that represents 1.2 amp and some minimum voltage. And realize going towards the right, the tube is conducting less to cut off. Going to the left, it's conducting more towards maximum current. So the operating line will start someplace over here, and we'll go up this way, over to intercept the maximum plate current, which will be two-third right there, someplace right in here. What's alluded to in care and feeding, but not thoroughly described, is that we absolutely must avoid operating over here in this region. We can't operate up and to the left of that line, because where those curves kick up are areas of extreme distortion. If you see further down, the lines going towards the left don't kick up quite so much. But whatever operating point is at that maximum plate current of 1.2 amp at whatever minimum plate voltage must be to the right of that line, or maybe worst case right on it. It's fairly obvious that correlates with a maximum grid voltage, because if the grid voltage goes too high, which means too much drive, that line going up and to the left is going to end up in this distorted region. And that's exactly what happens and causes distortion when an operator puts too much input power to an amp and it splatters. This is the splatter zone. Interestingly enough, compare that calculated 400 milliamp figure. We thought maybe we were kind of winging, to the operating case. Single tone plate current. Single tone means a single sine wave input. Exactly 400 milliamps. So we're fairly sure that we have landed one of the points of data from this operating case on this graph, or when we mark the point. The initial problem is to get the first point, or point 1, as referred to in the care and feeding, and that's care and feeding part 3 in the first part of the document. We've got to land the first point that coincides with the maximum plate voltage. But there's a trick here with this power grid tube in ground-to-grid service. When the tube has filament voltage and plate voltage, it's going to idle right about here. That's at a rated, on the case, 0 signal plate current, 62 milliamp DC. That's going to land up there. But in operating, that's not the case. And if we start off with point number 1 there, we're going to get a mistaken load line. What happens is that in operation, the plate voltage, or the grid voltage, is swinging from probably around 80 volts minus down to 0 and 80 volts plus. So with this grounded grid amplifier, with about an 80 volt swing either way, the grid voltage is guaranteed to go through a condition where at minus 10 volts on the grid, at 2 kV plate voltage, the plate current is 0. It's guaranteed to go through that condition because it'll go much further. Oh, correction. That's plus 10 volts. That's down's the positive direction. It will go much further than that into cutoff. So the load line must start at the intercept between 2000 and 0 amp. And I'm going to end this video and start with part 2 next.